Propulsion, the power that allows the Air Force to reach out and touch anyone, anywhere in the world and beyond. The Air Force Research Laboratory's Propulsion Directorate is the nation's premier organization to create and transition technology for military propulsion and power systems. Its mission is to create and transition propulsion and power technology for military dominance of air and space. The Propulsion Directorate is located at Wright-Patterson Air Force Base, Ohio, and Edwards Air Force Base in California's Mojave Desert. The Directorate has a long history of providing propulsion and power technologies for military aircraft, missile systems, intercontinental ballistic missiles, space launch systems, and spacecraft. The Directorate can trace its roots back to 1917, having a profound impact during World War II, providing the power plant technology base for all of the now famous aircraft of that age. The Directorate laid the groundwork for the transition to the jet age. It developed jet propulsion for all of the Air Force's fighter, bomber, and cargo aircraft, from the first P-80 Shooting Star jet fighter, the B-47 Stratojet strategic bomber, and the C-141 strategic transport, to today's F-22 Advanced Tactical Fighter, the B-2 Stealth Bomber, C-17 Globemaster III, and tomorrow's Joint Strike Fighter. Shortly after the jet age came to full throttle, the nation became embroiled in the space race. The Directorate was right there, helping to develop technologies and systems like the F-1 liquid rocket engine to power the Saturn V, to today's Titan IV solid rocket motor upgrade and the Space Shuttle main engine. The Directorate not only helped to put payloads in orbit, but provided the propulsion for those satellites for orbit maintenance and satellite maneuvering. The Directorate was also on the front lines of the Cold War, with the development of the Atlas, Thor, and Minuteman ballistic missiles. It was also instrumental in helping to win the Cold War by developing the technologies for the peacekeeper ICBM and making the Star Wars concepts reality.
Position and lock on.
The Directorate's research efforts encompass everything from basic research to exploratory development to advanced development. Basic research uncovers the fundamental principles and identifies new propulsion and power technologies. Successful technologies are then scaled up in exploratory development, demonstrating that technology can be applied to meet real-world needs. Finally, advanced development prepares and demonstrates the technology for transition to an operational or future system. The Directorate consists of 4 technical divisions and the necessary support divisions. The Propulsion Sciences and Advanced Concepts Division conducts research and development in combustion, fuels and propellants, systems analysis, lubrication, rocket materials, and hypersonic technologies. The Turbine Engine Division develops turbine engine components and gas generators and demonstrates these technologies in large-scale tests. These technologies are applied to jet aircraft and expendable applications like the cruise missiles. The Rocket Propulsion Division develops rocket motor components, solid rocket motors, liquid rocket engines, and spacecraft propulsion systems. These are scaled up and demonstrated in large-scale demonstrations. The Power Division researches and develops promising power processing technologies for power generation, management and distribution, energy storage, and thermal management. These technologies are transitioned into aircraft, weapon, and space systems. The technical divisions integrate and focus their work into 4 major thrusts. Air propulsion involves aircraft propulsion and air-launched missile propulsion. Space propulsion covers the spectrum of launch propulsion, orbit transfer, and satellite maneuvering. Aerospace, the newest thrust, is investigating revolutionary technologies needed to make military space operation vehicles possible. The power thrust provides power for aircraft, weapons, and space systems. To accomplish this extensive research and development task, the Directorate establishes strategic alliances with NASA, industry, other government laboratories, academia, and international partners. IPTET is an alliance with NASA, Navy, Army, Office of the Secretary of Defense, DARPA, and turbine engine propulsion industry partners. The goal of IPTET is to double turbine engine capability by improving affordability, performance, and durability early in the 21st century. IPRIT is a similar alliance with NASA, Navy, Army, Office of the Secretary of Defense, and numerous propulsion technology providers in industry. The goal of IPRIT is to double rocket propulsion capability by 2010 by improving hardware and support cost and increasing performance. Whereas past R&D efforts frequently chased after specific design points, which change with great frequency, both IPTET and IPRIT are designed to increase the entire design space, increasing it in phases, each one building upon the previous phase. In both programs, components are developed at the exploratory research level and are integrated into appropriately sized integrated advanced research demonstrations that are used to demonstrate achievement of the goals for each phase. The Component and Engine Structural Assessment Research (CSER) engine and the Integrated Powerhead IPD engine are two examples of demonstrators used to substantiate the attainment of the phase goals. The CSER integrates components such as metal matrix composite actuator rods, improved control logic, resin transfer molded organic matrix composite stator, and a probabilistic rotor and test them at full scale. The IPD engine integrates advanced reduced part count liquid oxygen and liquid hydrogen turbopumps, hydrostatic bearings, oxygen-rich preburner, and nanophase aluminum housing into a single engine for demonstration of the goals. Another directorate strategic alliance involves the development of high-energy density matter. The directorate has pulled together a world-class research team from industry and academia to develop next-generation rocket propellants. The task is to identify and characterize high-energy compounds that can be applied to rocket propellants, produce promising compounds, scale up and test these compounds, and finally, transition the successful compounds to propulsion systems. The Directorate boasts over $1.5 billion in premier test facilities that are a very necessary part of conducting the Directorate's propulsion and power research and development efforts. The Directorate has 19 liquid rocket engine test stands capable of handling up to 8 million pounds of thrust. Some of these stands were used for the F-1 engine development and test program that powered the nation's Man on the Moon program. Boeing's Evolved Expendable Launch Vehicle engine is being tested at the very test stand that tested the first Atlas ICBM, now the Atlas launch vehicle. The Directorate's solid rocket motor stands number 13 and can handle motors up to 10 million pounds of thrust. Recently, the Titan IV solid rocket motor upgrade was tested at the Directorate. The Directorate can test rocket motors at simulated altitude, handling motors ranging from millipound thrusters for space systems to 60,000-pound thrust ballistic missile motors or upper stage engines. The Directorate can simulate space environments up to 650,000 feet altitude, simulating the hot and cold extremes of space. The Directorate's Edwards Air Force Base site, located in the Mojave Desert, is perfect for conducting highly hazardous testing like the Space Safety Study to determine the hazards associated with large space launch systems. The Mojave Desert affords over 345 days of clear skies, providing plenty of power for the Solar Propulsion Lab. The only U.S. solar facility using liquid hydrogen, providing a 10,000 to 1 concentration ratio and 3,400 degrees Kelvin gas temperature. The Solar Propulsion Lab, along with the Electric Propulsion Lab, are developing technology for satellite propulsion, making possible 500% improvements in satellite maneuvering capability over current systems. The Directorate also has numerous facilities to support turbine engine and power processing research. The Compressor Research Facility conducts and supports exploratory and advanced development efforts in compressor technology, independently evaluating full-scale, multi-stage, single-spool dual flow fans and compressors under operating conditions similar to an actual flight profile. The Turbine Research Facility is used for exploratory development of advanced turbines. It simulates all important engine conditions through the use of aero and thermodynamic similarity in short-duration, transient research procedures. Combustion diagnostics facilities are capable of studying both subsonic and supersonic combustion in jet engines. The Directorate is the premier facility for the development of new fuels and lubricants, including the recent JP8 Plus 100. Plus 100 is an additive that cleans the engine components it flows through and also helps to cool engine lubricating oil, hydraulic fluid, and aircraft subsystems. Use of JP8 Plus 100 significantly reduces the maintenance on the engine. Nearly every U.S. military jet will use the additive. Even commercial airlines are considering its use to reduce engine maintenance. The Fuel Simulation Facility can simulate the fuel system of any aircraft, even today's F-22. The Electric Laboratory is used to study and evaluate all aspects of advanced power generation, distribution, conversion, and motor drive technologies. It has three 350 horsepower drive stands with a top speed of 30,000 RPM, all of which can be operated manually or controlled automatically by a VAX computer. Additionally, the facility has a wide assortment of high-power electronic components, particularly all types of capacitors. The High Power Laboratory supports the development of materials, components, and systems for application in the presence of very high electric fields or currents in electrical systems for various Air Force and DoD missions. There are three major high-power continuous DC power supplies that are capable of supporting a variety of research and development tasks, including development of high-current conductors, lightning simulation, and testing of high-power components. The Directorate has numerous plasma deposition systems at both the Edwards and Wright-Patterson sites. These are used to develop new semiconductors, coatings for high-temperature applications, lasers, high-power switches, plasma diagnostics, power generation, and combustion diagnostics. Finally, the Directorate has all of the necessary bench-scale laboratories to conduct its basic and advanced research and development. Hydrostatic bearing technology uses the liquid rocket's propellant to support the bearings on a turbopump to eliminate friction and increase part life. This technology is also being evaluated for large commercial air conditioning systems to decrease wear and reduce costs by an order of magnitude. Hybrid polymers, a cross between hard and brittle ceramics and flexible organic polymers, are being investigated as potential insulation and nozzle materials for high-temperature applications in rockets and turbine engines, as well as potential applications in the medical field. There are numerous other applications for the technologies found in rocket motors across the full spectrum of human interest. A number of the Directorate's technologies hold promise for electric and hybrid electric vehicles. Applicable technologies include lithium-ion and lithium polymer batteries, high-power solid-state switches, capacitors, power controllers, and rechargeable climate control systems. Other non-automotive commercialization efforts include high-temperature polymer capacitors, diamond-like carbon capacitors, supercapacitors, online oil condition monitors, and carbon-carbon rolling element bearing cages. For example, the polymer capacitors can be used for filtering in power supplies and generators, or as energy storage for medical defibrillators, welding, oil drilling, and lasers. The online oil condition monitor was developed for jet engines to provide real-time data on the condition of lubricants to determine when it should be replaced. However, this miniaturized, ruggedized infrared spectrometer can be calibrated to analyze virtually any fluid. Therefore, it is finding applications in such diverse fields as chemical manufacturing, environmental monitoring, and product quality control for food processing. The Propulsion Directorate is the source for propulsion and power technology for the Air Force and beyond. The Propulsion Directorate works with its many military and civilian customers and partners to develop technologies to meet their current and future needs, from failure investigations on existing systems to upgrades of existing systems, to technology for future systems.
All stations confirm readiness for test sequence by saying go or no go. Go, go, go.
The Directorate has the people and the facilities necessary to achieve its mission. That's to create and transition propulsion and power technology for military dominance of air and space. The Air Force Research Laboratory's Propulsion Directorate has been instrumental in maintaining the nation's military and economic superiority, providing propulsion and power to over 130 military and commercial systems in just the last 40 years. The Propulsion Directorate will remain America's leader in military propulsion and power technology, assuring superior, dominant air and space systems well into the 21st century.